All right, welcome to another tutorial for the bonus round, the bonus opportunity. I did a problem previously for the kinematic analysis, so this is the second video where I want to do a kinetic analysis, and I chose this example from class 17, I think it's 17, yeah, where we have work and energy. And we're going to, from this work and energy, find the angular velocity of the bars after we've released it. So I've already built the components. One thing that's important to do after you've built the components is to go to Evaluate and go to the mass properties. You can override these mass properties, and I've done that here. I made it 12 kilograms. I also made the moment of inertia equal to 4, matching what we've calculated it to be. And note that it'll give you like a little bit of a trouble. You have to make these even out, right? So it'll give you a message if you don't. But these need to equal, like, two of these need to equal the other one, otherwise it'll give you an error message. So the really one we care about is about the z-axis, so it'll accept it after you've made sure you fix that. So let's see, I will get rid of my most recent, no, not that one. I need to close this one down, right? So I don't need to save him. So here I'll start up a new assembly. And I won't put any parts in just yet. I like it if you can give me a white background. I prefer that. Change the units to, this problem is in meters, so we'll change it to meters right there. And I will insert a component. Now I have made a ground link. That's this guy right here. And I made him green because that's a good color for ground, right? Green and ground matched, G-R-E. Remember the first part that you put into a SolidWorks assembly will be fixed. If you want to change it, you have to right click it and float, but we're going to leave this one just where it landed. That's fine. And I'll put in the components, the link right here. Put that link in. I got to do it again. I want two of the same part. I think that's the one. Oh, there you go, link, yep. And then I made a rotor, not a roller, a roller. I don't want mates, I want a component. A roller, I can't say the word. Made a little roller. And one thing of note is if we open up that roller, I think I actually might already have it opened up. Let me see, do I have it open up? Yes, I do. Under its mass properties, under the evaluate and mass properties, I made the mass, I overrode the mass and made it really, really, really small. So 0.00001. So because we wanted, and the problem says to ignore the mass of the roller, so we had to try to make that match up. And here's the one we want to go back to. All right, so I'm going to get my mates to get this thing set up, and so I'm going to mate the front face of that with the back face of him. And make these concentric. And that face with the back side of that. And then I'll make these concentric. Uh-oh, computer's starting to slow down. I'll make those coincident. And then I'll make these concentric. All right, and then I waited to the end to make my last two mates. Well, okay, I'll make this mate right here. I'm going to make this one, that face, tangent to that face. It should know it. Yeah, it decided, it did it automatically. And then the last one, I purposely made it the last one because I'm going to suppress it when I go to make the dynamics, as I'm going to see if I can lift this guy up here. Lift him up some. And then make the angle that's formed between that bottom and this. It'll first try to make them parallel. But I'll come over here and click on that angle and make it 60 degrees. Now, of course, that needs to change when we go to the set it loose. All right, so we got all of the mates done now. Get rid of him, and we're ready for our kinetic analysis. So I'm going to go over to the motion study, and I just want to make this a little wider, a little taller, a little wider. Now I'm going to remind you, the first thing that you should do is to turn off this display. Right click on that orientation thing and click disable playback of view keys. That'll help you out so that things don't jump around. It'll always revert right back to your original view otherwise, but now you have the option to move the thing around. And let's see, I want to change this pull down from animation to motion analysis. If you don't see that available, you need to do it as an add-on. If it's not available as an add-on, you have to use another computer that has a different SolidWorks on it that has motion analysis available, because it's an important thing to be able to capture the physics. Notice that it's right here. SolidWorks motion in the add-ins needs to be available. Okay, so what's the next thing I want to do? I think I'm going to pick a time that this is going to go to. All right, so I grab that top black key. It doesn't want to go to where I want to go. Then I know that 1.5 seconds is going to be enough for me. And I can zoom in so I can see what that looks like right here. And also, we want to be careful. Any changes that you make, always make it with this slider as all the way to the left. Otherwise, it will make that change at whatever position the thing is at. That's really annoying. So right click onto this mate at the very bottom and suppress it, because we don't want it anymore. Now let's see, the thing I'm going to go to make a spring next, and I'll make a spring, and it's going to go between this point and that point. And I already made points as sketches on top of my link. Within the link, I made purposely made a sketch that I just drew on top of it, so that there would be a point where I could grab a hold of it. And you can see there's already a preview of the spring. If you want to change what that looks like, it's down here, but it doesn't really make any effect. What really has any effect is this guy right here. I want to change this K, and you'll notice that the spring constant is 20 newtons per meter in the original problem. So we'll change that, 20. And then the original length, it actually knows the length between these two parts right here. So that they assume that's the unstretched length, but we're told it's 1.5 meters. And I'm pointing as if you can see my finger, but you can't. And we don't have a damper or anything else in here. So notably that we could make a dynamics problem, a vibration problem, by having a damper in there. That's a interesting problem. You could consider doing that problem too. I don't mind. Do that problem. Do a dynamics, a vibration problem to compare. All right. So unfortunately, the spring one preview went away because I kind of liked it. We want to make gravity. Gravity needs to be involved here. It's in the Y direction in this view. For whatever reason, a lot of times that arrow will be very obvious, but it disappears in mine. You can only see the little green thing in the lower right-hand corner over here. It doesn't even show the arrowhead. But they give the value 9.81, which is what we would expect in metric. And I'm looking for other things. Okay, the 1.5 seconds is enough, I had found out, for this thing to go to horizontal, but I want it to not pass through the piece. So I'm going to go ahead and make contact groups. I'll make it between this guy. Well, first off, I'll change my selection thing and use contact groups like that, right? I like to hit that contact groups. And I'll have a contact group between this and that. All right. And we don't need to change friction, but I want to put the coefficient of restitution. Let's make coefficient of restitution 1 so we can watch it bounce. And I believe I have everything ready to go. The only thing I might change is my properties here, and I'm going to give it 200 time steps per second, frames per second, and I'm also going to hit precise contact. Let's see if that has works out well. So I'm going to hit calculate, and boom, it went. So let's take a look. I'll slow down that animation. Okay, worked out pretty well. Let's take a look at what the results are. So a good approach here, because this is going to be, we're looking for the results when this thing is equal to theta equals 0. So let's get the angle as one of the outputs of this. So I picked displacement. Oops, is it going to do it? Yeah, displacement. And I'll go angular displacement. And magnitude is our only option there. And I'm going to do it, pick two things, that guy and this guy. So that'll show us the angle between the two, I believe. And we'll plot it out. We can see it kind of makes sense of the change of the thing. But now I will add to this plot so I can have it as an output the angular velocity, because that's really what we're looking to find. And we'll have the z component because it's z is coming out of the page, so that's what we're referring to. And I'm just going to have that whole part. It's picking as a face. I kind of wanted to pick it as a thing. I don't know. I don't think it matters. It's the same angular velocity everywhere, so that should be fine. And I'm going to add it to an existing plot, the one that I have over here. And we can see the results there. But let's get the numeric results. So I'm going to pull this down. Come on down. And we'll go export to Excel. And it should come up. Okay, there we go. And let's turn all these into, should have 250, something like that. 300, okay, 300 time steps. Let me change the number. I just like to see the numbers. I don't like it scientific when it comes to looking at my numbers. There we go. So we want to find where it gets as close as we can to 0 degrees. And you might want to change the time steps to be able to get where that happens. All right, so right here looks to be where it's making the transition from positive to negative degrees. So this is like the results where we want to get here, and it's giving the output in angular velocity in degrees per second. So we want radians, so I'll turn radians, hit the radians command in Excel right there, and we'll see, oh look at that, negative 2.95. and boom, right there. So right there is the answer. -3 is what we were expecting to get. Actually, what I call it is 2.999, but this is clockwise, and you can see that this one is counterclockwise. So, and then they're going to be equal to each other. So we've got results that we expect. It makes a pretty good comparison. Other outputs that we might want to look at for the kinetics. We might want to find the forces in between links. So I kept this one open over here. So this is the one that we used for, or I thought we did. Where'd you go? No, this one. We used for the kinematic analysis right here. But things we might want to, we could get the reaction forces in between points. Or we could find what the torque is of this motor, right? So there was a motor that was driving this, and we can open up our present results and go to forces and then down to motor torque and go to Z component if we want, or just a magnitude if we'd like. And then we click, we have to go down to this tree, find the motor. We could plot it out. And so this is what the torque is is required. Now I didn't establish any of the mass properties of any of these links, but they do have mass properties. So this is the torque that this motor would take to be able to do this. We might also want to find what the reaction forces are at any particular pin. For that, instead of the motor here, we go we can go for reaction force, and we can pick a constraint. So I'm just going to go to the magnitude, and I'll look for this one right here. So we can see that it gave me a preview that was the force we're looking at. That was the mate we're looking at, and we could take a look. And so here are the magnitude of the forces that are taking place at that pin. So if we had done a free body diagram of this crank and we wanted to find what the reaction forces are, this is the one that we would compare to that. So hopefully this was useful and will help you work through a problem to model it and compare the results. 17 minutes.